All right, so for today's video lesson, we're going to get into topic 16.3. This is radioactive decay rates. So, generally speaking, the radioactive decay of a specific nucleus is unpredictable. However, the probability of any given nucleus decaying in a unit time is the decay constant. And this is going to be unique to each element. Okay, and the decay constant may be used to determine the activity or decay rate of a given sample. And this is often recorded in decays per second or in becquerels. Remember, becquerels is the SI unit for radioactivity, right? And that just says how many nuclei are decaying per second. Per second or second minus 1, right? So the decay constant, so that's going to be lambda here, okay, not to be mistaken for the wavelength. So that is the decay constant for an element. Okay, and this tells us the probability a nucleus will decay in a given time. Okay, so just an example here. The decay constant is unique for each element. So for radium, this has a decay constant equal to 1.4 times 10 to the negative 11 per second. So if you have a sample of radium, the probability that one nuclei will decay in 1 second is 1.4 times 10 to the negative 11. Okay? Now, typically it is hard to predict when one nuclei in particular will decay. We're going to use half-lives instead. Okay? Typically half-lives are used. It's a more accurate way to measure the decay rate of a radioactive sample. Okay? You guys do need to know this decay constant formula. Okay, so delta N is going to be the activity measured in becquerels or decays per second. Okay, N, this N is going to be the amount of radioactive nuclei. Delta T is going to be my time interval. And lambda is our decay constant. Okay, so you are going to need to use that formula in one of the practice problems that is your assignment for today. Okay, so make sure you know the decay constant and what it represents for a sample. Okay, so like I mentioned, because it's hard to predict when one nuclei in particular will decay, scientists use half-lives instead, and this is the time required for half of the nuclei in a sample to decay. So instead of looking at when one particular nuclei will decay, scientists look at the entire sample and measure the radioactivity in terms of half-lives. Okay? So if you look at the chart on the right here, we have some forms of radioactive elements, and then we also have the half-lives there, right? So we'll notice that uranium-238 has a longer half-life than thorium-234, okay? And half-lives are going to be unique to each element, just like the radioactive decay rates, okay? So we usually focus on half-lives, and there is the formula there, so we'll get to there in just a minute, okay? So, for half-lives, so graphs used to illustrate half-lives are going to represent an inverse decay, right? Instead of exponential decay, it's inverse relationship. So we start at the top, so our N naught is going to equal 100%. That's how much of radioactive material we have. Now, after 8 days, which is going to be the half-life for iodine 131. So after 8 days, the sample is going to be 1/2 as radioactive as our original. Okay, so then 8 more days elapse, and then that radioactive level is going to decay by half again. So then we're going to have N is equal to 25%, and that continues. So 12.5 and then 6.25%. Yeah, so this is an inverse squared relationship. Right? It has exponential decay or exponential reduction. Okay, half-life graphs will take on various forms because they're going to have different durations of their half-life. Okay, but they're all going to have this same shape. Okay. So most of the mass of the original isotope or parent atom from last lesson is intact as the decay occurs. But this is going to be transformed into that of another isotope or daughter atom, which may be stable or may itself be unstable and it would decay. Remember last lesson we talked about the radioactive decay series. If the parent nucleus decays into something that itself is unstable, it will then it will decay again until we find a stable nucleus. All right. So here is our half-life formula. So the mathematical relationship between the amount of radioactivity of the original sample, the remaining sample, the time passed, and the half-life is as follows. Okay, so N after a period of T is equal to N naught, which is the original, or the amount of nuclei in the original isotope, multiplied by 1/2 to the exponent T divided by T half. So that is the time elapsed divided by the half-life. Okay, so NT is the number of nuclei remaining after time T. N naught is going to be number of nuclei in original isotope. T is going to be the time elapsed. And lastly, T half is the half-life of isotope. All right, so there's our formula. That's what our variables represent. So let's get into solving one here. Okay, so calculate the age of a rock sample that has 1/16 the original amount of chlorine-36, given the half-life is 3 times 10 to the 5 years. Okay, so we are trying to find the time that has elapsed. N naught, the amount of radioactive sample, is just going to be 1. Our NT, or just our N, is going to be 1/16. And we know our half-life is 3 times 10 to the 5 years. Okay, so we are solving for T. Now, if you guys want to use your log skills here, you are more than welcome to. I'm going to use common bases here to solve for my T. But if you're confident with your logs, then you are more than welcome to solve it that way. Okay, so we have set up our variables. Now let's write down our half-life formula. So N is equal to N naught times 1 over 2 to the exponent T divided by T half. Okay, so I am going to isolate for 1/2 T divided by T half. So I'm going to divide both sides by N naught. Now I'm left with N divided by N naught is equal to 1 over 2 times T divided by T 1 over 2. Okay, N is 1/16 and N naught is 1. So 1 over 16 divided by 1. Any number divided by 1 is just going to be that number. So 1 divided by 16 divided by 1 is just going to be 1 over 16 is equal to 1 over 2 times T divided by T half. Okay, now to solve for that variable, we need to ask ourselves, how can we get 1 over 2 to have a identical base to 1 over 16? So I'm just going to say N is equal to T divided by T 1 over 2. I'm just going to change that for an N. Okay, so what value of N will give me, will make my 1 over 2 bracket equal to 1/16? Well, when my N is 4, when N is 4, those equations will equal one another. Therefore, so N is equal to T divided by T half. And we know our N is equal to 4. And we know our half-life is 3 times 10 to the 5 years. So let's solve for T here. Multiply both sides by T half. Okay, and then we'll be left with T. So T is equal to my half-life, which is 3 times 10 to the 5 years, multiplied by N, which is 4. And then we get a T equal to 1.2 times 10 to the 6 years, which is the same thing as 1.2 mega years, which is the same thing as saying 1.2 million years. Okay, so we have a little bit of logs here. Now, I am not going to be mean on like a quiz or an assessment or anything like that. So I'm going to make if you have a question like this, I'll make your n value really easy to find. Okay, so don't worry too much about that. Okay, yeah, for our other three examples, we know both our t. Oh, the next one we're actually gonna have to solve for t, but the remaining two, we will know our t and our t half-life. Yeah, so if you're having, if you see this question on an assessment, I will make your n value nice and easy. Okay? Alright, so calculate the age of an arrow if its wooden shaft has about 25% of the carbon-14 that is in a living tree branch, given that the half-life of carbon-14 is 5,730 years. Okay, so let's write down what we know. So T is what we're looking for. N was the original, or sorry, N is what we have now, so it's approximately 1/4. N naught is going to be 1. And our T half, our half-life, is 5,730 years. Okay, so we're going to use our half-life formula. So N is equal to N naught multiplied by 1/2 times T divided by your half-life. So let's get N and N naught to one side. So N over N naught is equal to 1/2 times T divided by T half. And let's say N is equal to T divided by your half-life. Okay, so I'm just going to rewrite this. So N over N naught is equal to 1/2 to the N. Okay, so my N is 1/4 divided by 1 is still going to give me 1/4, right? 1/4 divided by 1 is equal to 1/4 is equal to 1/2 to the N. Now what value of N will give me an identical base to 1/4? If we have at our N equals 2, 1/2 to the exponent 2 will equal 1/4. Okay, so if we know our N is equal to 2, now we just need to substitute that back into our formula right here. So 2 is equal to T divided by 5,730 years. Multiply both sides by 5,730. And we'll get a time or an age of 11,460 years old. All right. Moving on. Okay, so in this question here, we know the duration of the half-life and we know our T. So we just need to find our N here. What percent of the sample is left? Okay, so what is remaining? So what is our N? N naught, we can just say that we have 1. The time that has elapsed is 100 years. And our half-life of strontium-90 is 29.1 years. Okay, so our formula, N, which is the amount of radioactive nuclei left, is equal to N naught times 1/2 times T to the exponent T divided by T half. So N naught is just going to be 1 times 1/2. T is 100 divided by 29.1. punch those into your calculator. You'll get a value of 0.09237. So this tells us that we have 9/100ths of our sample left, but we want this as a percent, so let's just multiply that by 100. We're going to get 9.24% remaining. All right. All right. So, tritium. So hydrogen 3. So this is hydrogen that has 1 proton and 2 neutrons. This has a half-life of 12.3 years. We know our N naught is 100 milligrams. And we are asked how much is remaining after 5 years. So again, we can just use our half-life formula. So N is equal to N naught multiplied by 1 over 2 T divided by T half. Okay, substituting our values. Our N naught is in 100 milligrams multiplied by 1 over 2. T is 5 divided by half-life is 12.3. Okay, punch those into your calculator and we should find that we have 75 milligrams remaining. Okay, so that is how to calculate half-lives, either to find the age of an artifact, or you can also find the amount of a sample that will be remaining after a certain time period. All right. So let's get into some applications of nuclear radiation. So you guys are probably most familiar with chemotherapy, right? This is where a patient will essentially be bombarded with radiation in attempts to kill the cancer cells. Now, chemotherapy is, I don't want to say outdated, but it's not necessarily the best treatment because it's like a nondescript treatment. It doesn't target one particular area within the body. It's irradiating all of the cells in your body in attempts to kill the cancer cells. Now, cancer cells will replicate at a faster rate than normal cells. Like if you have a tumor, that is because you have a collection of cells which are replicating faster than normal, right? So radiation attempts to kill cancer cells, and this is because radiation, beta or alpha or gamma radiation has energy, right? And this energy can interact and interfere with cell replication and growth. Okay, so we just talked about chemotherapy. Now, as we become a little bit more sophisticated with our science and medical imaging and stuff like that, we're getting better techniques so we can kind of have a localized treatment if there's just like a collection of cancer cells in one area as opposed to irradiating the whole body. Okay, so where do we want to start? Let's go at patient in a scanner. Okay, so how this is going to work, the patient will be injected with some form of a radioactive tracer. This tracer does not really affect the cellular processes, but it's just going to allow your blood vessels and your neurons and other important tissues in your body to be imaged by one of these scintillation detectors. Okay, so by putting a radioactive tracer into your body, it can allow scientists to image what's going on in your cells a little bit easier. Okay, we also have IV radiation therapy. So in this case, you're going to have a irradiated solution. That's what we see in this bag here. Okay, and that is going to be pumping radioactive material throughout your bloodstream, and that would likely be in attempts to kill those cells which replicate faster than normal growing cells, so i.e. cancer cells, right? Machine radiation, so again, as we're getting a little bit more sophisticated with our instrumentation, we can have more precise applications of radiation. So instead of chemotherapy for the entire body, they can take a radiation beam and focus it right on one tumor. Okay, so just a little bit of a background on a few applications of nuclear radiation. I would encourage you guys to read pages 814 to 816 and 837 in your textbook if you want a little bit more information on this. Radiation is also used to kill bacteria and insects and in foods. Okay, so if farmers will take off a crop of, say, strawberries, and instead of treating these with antibacterial compounds, right? Instead of treating them with, antimicrobes, which could lead to antimicrobial resistance, they're going to use radiation to kill some of the bacteria that could potentially make us sick for foods. Okay? This is starting to become a little bit more popular, especially as we are a little bit concerned with the increase in microbes and bacteria which are becoming resistant to some of the antibiotics that humans have previously used. So this is a good solution for that. Of course, people are slightly concerned about radiating your foods to sterilize them, because then they are going to think that their food is radioactive, right? Which we don't want. We don't want to eat radiation. So scientists will develop different types of seeds to produce better crops. One of the ways they can do so is by irradiating the seeds. Okay, another strategy to mutate seeds is by cross-pollination or selective breeding. That is something that I'm a little bit more familiar with. This is where you take you take pollen, which is essentially sperm, and you would take ovaries from plants which have desirable characteristics. You would breed the two in attempts to get both of those characteristics into one plant. Okay? Now that's been done for decades, right? So we've done that, but now we can also mutate our seeds with radiation to produce better crops. So for example, navel oranges are a mutation from an orchard, sweet oranges from a monastery in Brazil from the 1820s. So the mutation in navel oranges will cause these oranges to develop a second orange at the bottom of the original fruit. Essentially, it's like a conjoined twins, right? From the outside, so this part right here is that like second navel that is being developed in there, right? Idea of this, if you just leave the navel orange, it is just going to continue to grow into a bigger and bigger orange, right? Navel oranges, I don't know if you guys are a big fan. I find that they're a little too fleshy. I would much prefer like a mandarin orange myself. Okay, but scientists can mutate seeds to produce characteristics which will allow the crops to perhaps have a larger yield than if they were just to use non-mutated crops. Okay, carbon dating. So we did a little bit of carbon dating, and if you guys are like, Mr. Jones, what is carbon dating? Well, this is what it is. Okay, so we know that we know certain half-lives of particular isotopes. So the known half-life of carbon-14 is 5,730 years. Okay, and this is a measure of activity from organic substances. This can be used to determine the length of something, of a living object or a dead object, maybe, like today. So if you were to find a sample, maybe a dinosaur fossil, right, you can measure the amount of carbon-14 that it has today, and based on the known half-life decay of carbon-14 and how much carbon-14 is present, you can estimate the age of that sample. Okay, I have a great video on carbon dating that you guys need to watch today. Okay, this is how carbon dating works. Yeah, this is an excellent video. This gentleman is from a podcast called it's called Stuff You Should Know. And they have like thousands of episodes ranging from how like violins work, or they go to how like quantum physics works. It's pretty interesting, and they have a wide variety of topics, so I would encourage you to check out this podcast. This is Stuff You Should Know. All right, so moving on. So what are some biological effects of radiation? Well, radiation is known to mutate the genetic codes of cells, so DNA, right? Radiation will mutate DNA. As a result, cells will reproduce at an uncontrolled rate. So that is like cancer, or faultily. This is where you have defects in body structures and or functioning. Okay, so this image here on the bottom right is a frog who has developed an extra appendage, right? So that is obviously not good. That'll probably reduce its ability to be able to reproduce and pass on its genes, which is good in this case because we do not want to pass on, genes that will code for frogs which have 5 limbs, right? So that's not good. Yeah, so you guys are probably familiar with this from first-hand experience. Maybe if you've gotten a sunburn, we'll talk about that in just a second, okay? So, yeah, radiation will essentially modify your DNA. And we know, you guys should know from biology, DNA makes RNA, which makes, amino acids, which makes polypeptides, which makes proteins, right? Now, if you have your DNA being damaged, the rest of this pathway will not be able to occur, right? If you can't read the DNA, you're not going to be able to make the appropriate RNA, and then you can't make proteins, which could be pretty fatal for us, right? So that's not good. Intense exposure to radiation can result in headaches, nausea, vomiting, bleeding, severe burns to tissue, loss of hair, and death. Okay, so this gentleman here looks like he has gotten some serious sunburn, right? That's actually kind of gives me the shivers just looking at it. Yeah, so when we put on sunscreen, there is a chemical in the sunscreen itself that will actually absorb like the ultraviolet radiation that is being emitted by the sun. UV radiation is ionizing radiation. So UV radiation can affect your DNA, right? And is what's happening when you get sunburned. Your skin surrounding the sunburn becomes red because your blood is flowing to that site where you have damaged tissues, right? And then what happens after a few days after you get a sunburn is your skin starts to peel. And this is programmed cell death. We call it apoptosis. And this is your body telling your skin cells to die because likely they have had damaged DNA. And your body, of course, does not want that damaged DNA to spread throughout your body. Okay, yeah, so if you have too much radiation, it's called radiation sickness. So the people who were around like Chernobyl likely would have died from radiation sickness. Okay, this image here is a pretty interesting one. So we have glowing mice. So anytime that an organism is able to produce its own light, we call it bioluminescence. And yeah, these mice are bioluminescent. So is what we see now with gene manipulation and gene encoding and stuff like that. Scientists have been able to insert a bioluminescence gene into mice, and they actually find that they're able to glow. So it's kind of freaky, to be honest. But yeah, radiation is not good. Radiation is not good. Okay, so this is an interesting story. So this is back in 2007. So Alexander Litvinenko, he was a vocal critic of Putin. He met with a former KGB agent for a cup of tea. And it is hypothesized that this former KGB agent dosed his tea with polonium-210. Okay, this is a radioactive element and it can cause death. So this is what happens when you speak back to Putin. So you can die by ingesting radioactive material. Not good. Okay, so yesterday we talked about the different penetrating ability of the three different types of radiation. So remember we had alpha, beta, and gamma rays were the three types of radiation we talked about. Now alpha radiation usually is not able to penetrate paper. And beta was able to penetrate paper, but not like a centimeter thick lead, right? Or in this case, not the thickness of a human hand, whereas gamma rays can pass through everything except for like 10 centimeters of lead, right? So yeah, although gamma radiation is associated with the highest risks due to its high penetrating ability, but beta and alpha radiation can still cause harm to tissue if it is emitted by a radioactive material that is ingested, absorbed, or inhaled, or if you were like bombarded with alpha rays from whatever radiation source and you weren't wearing a t-shirt, that would potentially be able to be absorbed within your body. Okay? So this image here, this is from the Environmental Protection Agency. I got this last week. So this is updated. And this just shows current or common sources of radiation exposure. So the majority of our radiation exposure is from background exposure. So that's going to be from like the Earth's crust, which has radon, right? Earth is actually slightly radioactive. Radon and thoron will be emitted from the ground because those elements themselves are unstable. Okay, if you fly in airplanes a lot, you are exposed to more radiation because of those cosmic rays being emitted from the sun. I was actually really surprised at the consumer. So that would be like iPads, cell phones, computers, and stuff like that. I was really surprised that only made 2% of radiation exposure. We also have industrial and occupational exposure. And then the other big one is when we're going to get like medical scans, right? So computed tomography, those are CT scans. Interventional fluoroscopy, conventional radiography, right? This is when you're going to get like a full body scan, maybe like a MRI or an X-ray or something like that, okay? So that's where the majority of our radiation comes from, is from medical treatments. The other half is just from background exposure from the Earth and a little bit from consumer, okay? So you don't need to know this. I just thought it was more for interest than anything. Okay, so that is it for today's lesson. So if you have any questions, you know how to reach me. Your assignment for this topic is page 817, questions 1 to 3, and question 5. Okay, so complete those for the remainder of today's class period, and please submit those to me when you get them finished. Okay, thank you, and have a lovely day.